Hello everyone, welcome to my remastered tutorial on creating a digital audio synthesizer. For the past few months I've been unable to record voiceover commentaries for videos, and while being inactive I've always wanted to complete the C# tutorial on a digital audio synthesizer. But now that I've gained so much knowledge over the past few months, especially on audio synthesis, I've decided to do a complete remaster. Some of the concepts used in the C# tutorial were pretty bad. For example, to play back the audio we generated, we would write a WAV file in memory and then play that using a WAV sound player. It was a pretty terrible idea because it was inefficient with memory and it would only play 1 second of audio. You couldn't extend it or play multiple different sounds at the same time with keys. But now I know how to do that. That's what we're going to implement in this remastered tutorial. I will be using Java instead of C# or C++ simply because it's the most popular language and I think the most people would want to see this tutorial in Java. But because C# is so similar, anyone from the previous tutorials can still follow along pretty easily. The prerequisites for this tutorial are a basic understanding of Java or some other similar object-oriented language such as C# or C++, and a basic understanding of digital audio in general, although I won't be covering the basics of digital audio in this tutorial. There will be a few keywords on the screen now, just so you can reference them throughout the tutorial. So first things first, I've created an empty Java project in IntelliJ IDEA, which is the IDE you'll be using for this series, and now we're simply going to create a main class, which will contain the entry point for the program. So we'll use the standard Java package naming conventions. And once it's created, we'll add the main method. So public static void main with string array as the arguments. And now we want to create a basic GUI class. We'll call it Synthesizer Remastered. This will be the base of the GUI we'll be using for the synthesizer. So we want to create a private JFrame. We'll import the swing libraries. We'll just call this frame. We'll set it to a new instance of JFrame called Synthesizer Remastered. We'll then create a internal constructor and we'll set a few properties of the JFrame. So the first one we want will be the default close operation, which will be dispose on close. The second, we want it to be the size, so set size, something like 613 to 357, and then we'll want to set the set resizable property to false, so we want it to be a fixed sized, especially because it will, in other synthesizers you can't really resize them because all the controls are in a fixed position. And another one will be the set the layout. Set this to null, we don't want a layout manager managing the layout. And the other one will be set location relative to null. If you don't put this, it'll appear in the top left of the screen, but we want it to be in the middle, simply so we don't have to move the mouse to the top left. And then finally, we will set its visibility to true. So now let's go back to the main method and we will call a new synthesizer remastered. Now we'll run this and see if it creates the application we want. There. Perfect. It's a decent size for the synthesizer base. And now we will start programming probably the most complicated part of the entire series in the first episode, which will be how we stream audio output from the generated samples we'll be making. So to get started with creating the audio streaming application, we'll want to download some libraries. This library we'll be downloading is LWJGL, which is a lightweight Java game library, and we only want one component for this. So head to the download tab and customize LWJGL3. We want the release build and we want no presets. All we want is the mandatory LWJGL core and OpenAL. OpenAL is AWJGL's binding to the OpenAL native interface, which is written in C or C++, I can't remember which one. This is what we'll be using to interface the audio playback from our class. So we'll want to download the zip, it'll build it for us, and drag it to our desktop or wherever you want, extract the files, and we'll get quite a few actually. We can delete everything that isn't a jar file and move these to the center, and we'll want to add them to a library file. So we'll go to the folder location, and where we have these folders here, I'll create one called libs, stands for libraries, and we'll want to drag all the jars we downloaded into here. Then back into the project, we will notice it's been recognized, all the files. We'll want to open them as libraries. And then if we check here, we should be able to reference these org.awjgl.openal classes. So the next thing we'll be creating is the class that will be interfacing the OpenAL libraries we've imported with. Basically this class, it will use samples that the synthesizer will generate. It'll store them in small buffers, so around 512 samples long. And these buffers of 512 samples will be stored in a queue to a source that we can send to a device. And as this is playing, one buffer, say the one at the front of the queue, will get played, and then it'll be sent to the back of the queue, and then it'll be refilled. So this queue has constantly been, the buffers in front have been emptied or played, and then sent to the back of the queue to be filled. This allows us to have a constant stream of real-time audio, unlike the method I used in the previous series if you watched it. If not, don't worry, because it was a terrible idea. Basically, we used a WAV file, or we opened one in memory, writ a header file, we writ a header chunk of data, metadata about the audio, and then put the samples in there. The problem with that was it was 1 second of fixed audio, so you couldn't press a key for a variable amount of time and have it playing for that length of time, and you couldn't press multiple keys, so you can have multiple frequencies of sound playing at the same time, which is very impractical for a synthesizer. So to create this buffer mechanism, we're going to create a brand new class. We're going to call it audio thread, and it's going to extend the thread class. Now in here, this is where we're going to be interfacing with OpenAL. We're going to want to import a few things. So we'll use org.awjgl.openal, and we'll want the AL class, and we'll also want the ALC class. With all this OpenAL stuff, you don't necessarily need to know how it works, you just need to know what it's doing, unless you want to get more into OpenAL, but we'll only need some basic functionality to do what we want to do in this series. So we'll want the AL10 class and the ALC10 class. You see, we'll use the import static, so we don't have to reference AL10 every time. We're going to be handling all the OpenAL interface in this class only. You won't see any more LWJGL in any other class. So it's okay to use static here, because it'll be contained all in this class. We won't need it anywhere else. So we want the ALC10 and everything inside of it. Next, we're going to want a constructor with no parameters for now, and we're going to want some private final fields. Now I'm going to explain why we want all the LWJGL OpenAL stuff handled in this class only, because this interface with OpenAL is very un-Java-like. It's more C-like, because it uses buffers and pointers and stuff. So we're going to want a new integer array, leave this blank for now, a long for a device, I'll explain what these are doing later. I want a context, and we're going to want a source, which is an integer. First we'll declare two constants. We want the buffer size, so how many samples each buffer will contain, and a buffer count, which will be how many buffers will be in the queue. So we want, for this device, we'll want 8 buffers that can contain 512 samples each. So for the buffers, we'll want the buffer count. For the fields below, we'll want to call some OpenAL functions. But first, I'd like to explain why all these, the device, context, source, and buffers, they're all native types instead of some object types, some custom device or context type. This is because OpenAL is written in C or C++, and those C languages, they use pointer values to point to location in memory where these things are stored. Now, obviously Java doesn't use pointer values. It doesn't support them because it uses managed memory, garbage disposal. So we need to reference this value or pass this value to the native OpenAL code we're interfacing with. So this is why these are number values. So the function we'll need to call to initialize these pointers are the ALC open device. You'll see it wants a device specifier here. This is basically, I don't know how it works internally, but it's just we want to specify what device we want to open. Now, we'll let the API decide this for us. So we'll use the ALC get string method as handle of 0. So no handle, basically null handle in referencing pointers. And the default device specifier. So we want to open the default device. For the context, we'll want to call ALC create context. Want to pass the device handle, and it wants an attributes list. So we want to pass no attributes, so we'll just pass a 0 in. So an integer array with of length 1, so it'll have one default integer value, which will be 0 inside. The context is basically everything you need to know about the device in its current state, just the context of the device. Self-explanatory. And before we can initialize the source, we need to call a few methods, such as ALC make context current. This just makes the context obviously the current context of the OpenAL instance. And next we want to call al.create capabilities. This wants some ALC capabilities, so we can simply call the ALC create capabilities method of the device. Again, this is self-explanatory. It creates the capabilities, or what the device is currently capable of. We need to do this before we call or we generate the sources, just so OpenAL knows what's possible and what isn't possible. Again, these methods, this one, the AL method, returns an AL capabilities object, but we're never going to actually use it in this, so we're not actually assigning it to anything. And now we can call AL source equals AL gen sources. So it's generated a pointer to a source, which is what we can buffer data to, what we can buffer all these buffer pointers to, which will be used to play back from the device. The next thing we're going to want to do is initialize the queue of buffers. The way we're going to do this is to create a new for loop and loop under every value of the buffer count. So for every buffer we want, and we're going to want a method that we'll create in the near future, which will be sort of a buffer samples method. I'll explain why later, but we'll also want to call the AL source play to the device, or the source, sorry, and then we'll want to catch any internal exceptions. Basically, the OpenALC code, it can't throw Java exceptions, so it needs to raise certain flags, set them to true, saying there's an error. So we can use sort of our own get error or catch internal error. We can use our own method to check what's gone wrong, if anything has done. And then since we've extended thread, we can start the thread. Next, we're going to want to implement the methods we've templated above. The first one being a private void called buffer samples, which we want to take a short array called samples, so the audio data we want to buffer, and we'll need to create a new field here. We'll call it buffer index, it'll be an integer. or we'll leave it to 0. Basically, this is going to form the queue mechanism I was talking about, where initially this is 0. We're going to buffer samples to buffer with the index of 0, and then increase this buffer index, so it'll go to the next buffer a sample, it'll go to the next buffer, all the way until the last index buffer, which will be 7 in this case. Once it's increased, it'll be reset to 0. So it's constantly iterating over each one and then going back to the start of the queue. So in here, we'll want to get the buffer pointer of the current index. So we'll want buffers of the current buffer index. And then since we won't be using this value, the buffer index again, we can increment it. So it's increased for the next time we use it. Now we'll want the al buffer data method. We'll want the buffer to buffer to. We'll want the al format of the mono 16. So a single channel audio that's 16 bits, which is the short value. Remember, every integer type's allocated a certain number of bytes depending on its size. So a short 16 bits, a byte's 8 bits, and an integer's 32 bits. So we want 16-bit audio for the shorts. We want the samples passed by the function, and it needs a sample rate, a frequency. So how many samples it wants to play per second. We'll actually write this in a utility class. It'll be called, let's call it public static class audio info. And in here we want a public static final integer, call it sample rate, which will be set to 44,100. So it'll be playing 44,100 samples per second, which you can then write this to Mr. Audio Info sample rate, and then we will queue the buffer to the source. So the source we want to queue it to, and the buffer we've just filled with data. And then we want to use the method here. We'll call it. It'll be buffer, not a method, but we'll call the modulo operator. This will do the queue. Or this will reset the value. Basically, this will reset this value of buffer index to 0. If once we've incremented the index, if this equals 8, it'll reset it to 0. So go to back of the queue. What I mean by this is, say buffer index was 0 and buffer count was 8. This is going to return 0. Because remember, the modulo is the remainder. Say we have this to 1, so buffer index is 1. This will also be 1. Same for 2. All the way up to 7, it's still 7. But when it hits 8, this will return 0. So it'll go right back to the start of the queue. The next method we want is, I didn't mean to delete that. And the other method, we can actually call this now, here, buffer samples. And for the samples we want to pass basically a dummy buffer. So we want it to add the 8 buffers we want, specified by buffer count, with no audio data whatsoever. So it won't actually play anything, but the source will have 8 basically buffers queued to it that have been processed and ready to be refilled with audio samples. The next method we want is the catch internal exception method. So we'll create another private void called catch internal exception. And the way we catch exceptions is we'll create an error pointer or a specifier, and we'll call the ALC get error. And it wants a device, so if anything's gone wrong at any point during the execution, an error flag will be thrown up on device. And then if the error doesn't equal ALC underscore no error, so if there is an error, we're going to want to throw a custom runtime exception, which I'm going to implement now. And here is this runtime exception. Basically, it's called OpenAL exception, extends runtime exception. The constructor, it wants an error code, And since if you call the base constructor of the previous or the super class, you have to include this method first. So I couldn't do a switch statement and choose, which string to format based on which error it is. So I just had to do a load of ternary conditionals. So what this is doing is, once we get an error code, it's saying internal and then deciding, is it an invalid name? No. Is it an invalid enum? No. Is it an invalid value? Is it an invalid operation? Or in some other weird case, it'll be an unknown exception, which I'm not expecting to ever happen. But it'll just finish off with OpenAL exception. So then we can call this, we can throw a new OpenAL exception with the error code we can pass to it. Then we'll simply go up here and catch an internal exception, if there is one. The next thing we want to do is override the run method of the thread class. Remember extending thread here. And this will be called once we start the thread, which you're doing automatically on the object's construction, since we want it to always be running. So we'll put in the override annotation. We want it to be a synchronized method, since we'll be calling the wait and notify methods of the thread. We want this to be run. And we'll want two new Boolean fields here. We want the closed and running. So we'll have two while loops while not closed inside here while not running. Before we proceed, I'm going to implement a new package. This will be the utilities package. And inside here we'll want utils and a interface called procedure. This is what I do with all my Java applications, and I'll explain why in a second. So I want a void invoke in procedure, which can throw an exception, and in utilities we want a public static void invoke procedure, and it will want a procedure as the parameter. And all it's going to do is try invoke the procedure, and in case of an exception, E, we're going to want to decide if we want to print the stack trace. So in here, if we want to print the stack trace, we will e.print stack trace. This just saves you writing every time you want to call, or every time you want to invoke methods like wait, which if you look here can throw a interrupt exception. Simply write utils.handleProcedure, and it stops you writing try, wait, catch, exception, and then e.print stack trace. Oops. Instead of doing all that, you can simply do utils.invoke procedure. I will rename this to handle procedure actually. It'll explain more of its purpose. And call the method reference this dot wait and false. We don't care about if there's an interrupt exception. So that's the difference between, or that's how simple things can be if you just put a handle procedure method. So what this is doing here is while it's not running, we want the thread to wait. It's more efficient than doing things like while not running sleep for 1 millisecond, because it'll still have to process the millisecond wait. And it's a lot more efficient than just constantly looping while not running, because it's going to be using all the system resources, just looping while continuously. So the next thing we want to do is, if the thread is running, we want to find how many process buffers there are. So we'll use al get source I, so get source information, and the specifier al underscore buffers processed. So once we first run this method, once we first start, all the buffers are going to be processed because we've played all the dummy buffers we put in here, and if or for each processed buff, so I is smaller than process buffers, we'll increment I. We want to somehow we want to retrieve a short array of samples. So I'll show you how we'll do this next, but we want to check if, we'll comment this out first since we'll do it later. If samples equals null, we want to set running to false. And then we can break out of this method. Otherwise, we want to use al delete buffers, al source unqueue buffers, source. So what this will do is it'll unqueue the most recently processed buffer and then delete it. So the buffer at the front of the queue. So once that's deleted, we can reference buffers of the buffer index, the current index, equals al gen buffers. So it'll generate a new buffer for us that we can then buffer samples to, which we'll do once we find out how to retrieve the samples that we're wanting. Next, we'll want to check if the source is currently playing. So we'll pass the source, get the source information, and source state. So if this doesn't equal al underscore playing, we will play the source. And then we'll just catch internal exception just to be safe. Now if we close the thread, we want to do a few cleanup operations. So remember the C code that OpenAL's written, and it uses unmanaged memory. So we need to clean all this stuff up manually. So delete all the references and stuff. So we'll simply call al delete sources, delete our source, al delete buffers, delete the buffers, destroy the context, and close the device. And now everything will be cleaned up. Now we don't have a way to specify running to be true. We don't have no way of actually running the thread. So how we'll do this is create a synchronize void, which will be called trigger playback. So this can be called by a synthesizer when a key is pressed, and all it'll do is set running to true and notify the thread, which will take it out of its wait state. Then it'll check if it's running, it'll realize it is running, then it'll continue to do all the processing and stuff. We should also implement a way of closing the thread, since we haven't done yet. So in here we want to set closed to true, and then we'll put a comment here because it's not very clear. We want to break out of the loop, so we can call trigger playback. Why we do this is so if we want to close and the thread is not currently running, we will break out of this. We will notify, we'll set running to true. It'll realize it's not running. There'll be no process buffers, so it'll skip all of this. And then it'll check, it'll reach the end of here. It'll say while closed, while not closed, and then it'll realize it is closed and simply destroy all the context and all the OpenAL specific stuff. Next, we'll want to implement a way of supplying the audio thread with all the audio data that the synthesizer will be generating. The way we'll do this is to create a supplier object. Want it to be a supplier that supplies a short array. Call it buffer supplier. And we'll pass this through the constructor. So just type the exact same, supplier of a short array, buffer supplier. Then this dot buffer supplier equals the past buffer supplier. Now we can go back to the run method where we can replace all these comments. So short array samples equals buffer supplier dot get. If the samples aren't null, then let's say if they are null, then we can set running to false because it's sent no data, so it's no longer running, and then we can break. Otherwise, we can do all these stuff here. We can queue a new buffer or generate a new buffer, and then buffer the samples that have been sent from the supplier. Next, we're going to want to implement a way of sending just example data for now, since we haven't got the synthesizer up and running with oscillators and stuff. So we want to send just a sine wave, basically, a fixed frequency sine wave. So the way we'll do this is create a final audio thread. We'll actually set this to final as well, so we won't be changing it. A private final audio thread. We'll set it to, just call it thread. And we'll initialize it to a new instance of an audio thread. Remember, it wants a buffer supplier, so we'll implement this now. So we'll create a field, actually, a private boolean called should generate, initially false, and a private integer wave pos. In here, we'll check if we shouldn't generate, and if we shouldn't, we will return null. Remember, it wants a short array here. Also, we forward reference this. This is just temporary, so we can remove this later once we've got the synthesizer a lot more functional. But if we want to generate, we will create a new short array and set it to the length of audio thread buffer size. So we want 512 samples. Now for every value under 512, so audio thread buffer size, we want to increment I, and we will set the position of the short array to, this will be creating a sine wave. So we want short.max value times by the algorithm to make a sine wave. So that's math.sine 2 times math.pi times the frequency of the sine wave, which for now will be 440, divided by audio info dot sample rate. We want to times that by the wave pos, which we can increment after. What's wrong with the wave pos? Oh, we've forward referenced it again. Remember, this is only temporary. And whether we'll then return the buffer we've created. Now we'll also need to create ways of setting or calling the trigger playback and stopping the playback, meaning we should generate to false, sorry. So the way we'll do this is add a key listener to the frame. So frame.add key listener. This is how we listen to keys. So we'll add a key adapter. We want to override key pressed and key released. Override these methods here. We'll put, if the audio thread is not running, we'll just create a property here. Put it up here. Boolean is running, which will return running. Why we need to do this is because if we call notify, so inside of here, if it's not running, we'll trigger the playback. If we call notify repeatedly, it causes weird behavior, which I can't really explain. So just to be sure, we'll reference our audio thread, which we've just called thread. I'll change that to audio thread. So if the audio thread is not running, then we should generate samples, and we will trigger the playback of the audio thread. On the other hand, on the key released, when we release a key, we should not generate samples. Also, we should implement a window closing event. Frame.add add window listener. This is because if we press the cross button on the window that's going to open, the thread will still be alive if we haven't closed the thread, and the application won't close unless we kill the thread as well. So this is how we're going to call we'll add a new key, a window adapter, sorry. So on window closing, we'll want to close the audio thread. So this will destroy all the OpenAL resources and allow the application to close on its own. So now let's start the application and see what happens. So when I press and release any key on the keyboard, it plays a 440 Hz sine wave of the time length I specify by how long I hold the key down. So you can play longer time spans or much shorter time spans. This has been part 1 of my remastered tutorial of creating a digital audio synthesizer using Java. Thank you very much for watching. In future episodes, we'll be adding a whole host of features such as different waveforms, oscillators, wavetables, LFOs, filters, basically turning this blank form into a very functional synthesizer that can synthesize a load of unique sounds and professional sounding sounds as well. So join me in part 2 where I'll be adding oscillators and some basic GUI form design so we can start to get some functionality and variation in the synthesizer. Thank you very much for watching, and I'll see you in part 2.